Hey everybody, today I'm going to be talking about Lab 4, Oscillations. The objective of the lab was to analyze the motion of a spring mass that was oscillating while swinging in an arc-shaped motion, then to take this video, upload it to Tracker to analyze its motion, and create a computational model to compare the two. The result was that the predicted motion of the mass from the computational model followed the pattern from the data from the video analyzed in Tracker. A possible error in the comparison was that drag force could have stopped it or changed the results. A conclusion is that the spring mass system satisfies the energy principle. Two physics principles that you need to know for this lab. The first one is Newton's second law, which states that the final velocity equals initial velocity plus F net divided by mass times delta t. The second principle is the energy principle, which states that the change in total energy equals a change in kinetic energy plus the change in potential energy for the spring plus the change in potential energy for gravity. Here are two calculations I did so that I could create a computational model. The first was to solve for the spring stiffness. I used the equation for the period of oscillation, which states T equals 2 pi times square root of m over k, where m is the mass and k is the spring stiffness. I reorganized it and solved for k, which equals 6.869 Newton divided by meters. The second calculation I did was for the relaxed length of the spring. I stated that the gravitational force equals the spring force in a equilibrium system, and from that equation I solved for the relaxed length to be 0.126 meters. Here is the energy equation that we'll need when considering the energy principle in the computational model. First, kinetic energy equals 1/2 mv squared. Second, the gravitational potential energy equals mgh. And third, the spring potential energy equals 1/2 ks squared, where k is the difference in the relaxed length from the length with the mass. Now it's time to look at the video. Here is the video that we analyzed. I set the origin of the video at the point of contact where the spring was fixed. I also had a calibration length which stated the length. Also, I tracked the motion of the spring throughout its oscillation period, and from that I got a table from Tracker that states the time of the position and the position in X and Y. From this, I uploaded this data to a CSV file and was able to create a computational model. In this computational model, I have the visualization and graph setup, which I did not change. Second, I have the initial properties, which states that the mass was 0.402 kilograms. Also, the initial position of the mass of the system, which was found from Tracker, and the initial velocity, which is 0, and the time starts at 0. I also read in the CSV file that I created from the Tracker's position versus time, and I set a delta t to be a very small value. Second, I initialized the constant g and the spring stiffness, which I calculated like shown before, and the relaxed length of the spring. Second, I found the length of the spring when the mass was attached, and corresponding to that, the value of S. Second, as shown before, I calculated the kinetic energy, the potential energy for gravity, and the potential energy for the spring, as shown before. Here is the loop where the calculation happens. I initialized the three energy equations. I found the equation for gravity, which I said before was m times g in the negative y direction. Then the force for spring, which is negative k sub s, which is the spring stiffness, times s, which is the difference in the springs, and times L hat. Next, F net was the combination of two forces. Then the position and velocity of the ball or the system were changed due to Newton's second law. Then I updated the location of the spring. This is because the spring location changes throughout its motion, so that Tracker can track it. Then I updated the energy principle, and this is so that the energy can be tracked throughout the motion. Now let's run the code. As you can see here, the red ball, which is the actual observation, follows closely to the computational model. The blue arrow is the spring force, which changes throughout the motion, and the black arrow is the gravitational force, which is constant. There is some discrepancy, which could be due to a discrepancy in the tracker, or it could be due to the drag force. By changing two lines of code, you are able to graph the energy principle. First line is that, and the second line is in the beginning, which allows me to graph four things in the same plot. Let's run this again, and you'll be able to see right here the energy. The blue line is the change in kinetic energy, the red line is the change in potential energy for the spring, the green line is the change in potential energy for gravity, and the yellow line is the total energy. As you can see, the total energy stays 0, and we'll discuss this later. Now let's answer this what does it mean question. The energy principle is satisfied because, as stated in this equation, the change in energy for the system is equal to 0, so energy is conserved, and according to this graph that I just showed, the yellow line, which is the total energy, is 0. Next, I compare the two oscillations for both the x position and the y position. The period of oscillation for the x position is 1.68 seconds, and for the y position is 1.52 seconds. The difference is 0.16. There's a greater difference in position in the x position graph than the y position graph. This is due to differences in the factors for which determine the x position and the y position. The y position is from gravity and the stiffness of the spring, while x position is the stiffness as well as the length of the spring. Thank you, and I hope you enjoyed my video.